My name is George Wang, and here is a presentation video on our work, Multi-Agent Automated Machine Learning. Recently, reinforcement learning has been validated to be effective to optimize individual AutoML modules, such as data augmentation, neural architecture search, and hyperparameter optimization. However, when facing a huge search space and the joint optimization of these modules, the efficiency and performance challenges remain. Through experiments, we observed that among ML modules there exists a cooperative relationship that facilitates the joint optimization of modules. Accordingly, we propose multi-agent automated machine learning MA2ML, which explores the cooperative relationship towards joint optimization. MA2ML takes each module as an agent and the final performance as a reward to formulate a multi-agent reinforcement learning problem. MA2ML is a general framework for joint optimization in AutoML. For ease of presentation, we use the joint optimization of data augmentation, neural architecture, and hyperparameters for image classification tasks as an example to elaborate MA2ML. We first define a search space, as shown here. For each module, we implement a controller to sample different choices according to its policy network. Each agent takes a random state as input and outputs a selected action. After all actions are determined, we train a network with the search pipeline settings on the image classification task for apples and evaluate top-line accuracy on the validation set. We take the accuracy as the reward for all agents. The objective is to maximize the expected reward. One method to solve it is to learn a policy individually for each module. We use the reward to directly guide the update of each agent's policy, and we term this method MA2ML let. However, if we use the reward to directly feed back to each agent cannot judge how good the selected action is. To solve it, we introduce credit assignment in ML2ML, adding counterfactual baseline to measure the marginal contribution of each agent. Besides, we incorporate off-policy learning, such that the current policy can also use historical experiences to further improve search efficiency. This is the framework of joint optimization with MA2ML. For AutoML training, the ML pipeline is formed by the actions sampled. Then it is deployed for training on the dataset and to obtain the reward. After that, the experience is stored in the replay buffer. For MA2ML training, a mini batch of experiences are sampled from the replay buffer to update the critic policies and target policies. For experiments on ImageNet, considering the search cost, we randomly select 200 classes to form the training set in the search process. To better balance the performance and computational cost of the search pipeline, constraints of flops are added in the reward. The results achieved by MA2ML and other SOTA works are shown in the table. All compared models have computational cost close to 600 million flops for a fair comparison. And the right two figures also show the effectiveness and the superiority of MA2ML. On CVPR, the results achieved by MA2ML and other SOTA works are shown in the table. We also implement MA2ML on policy on CVPR10 as an ablation, and the red figure shows the search efficiency improved by off-policy learning and the effectiveness of credit assignment. In conclusion, we propose MA2ML, a general framework for the joint optimization of ML modules, which transforms the joint optimization as an MARL problem and yields SOTA top-line accuracy on ImageNet under several constraints of flops. MA2ML has several advantages. It can be generalized to more modules in different tasks, and is agnostic to search spaces. Besides, MA2ML directly optimizes the reward instead of loss, so the incompatibility of different modules that may exist based on training loss is naturally avoided.